So this is a flowchart which goes through like a hypothetical use case of animal migration. And it contains like the abstract steps that we need to take. Um, and it is also categorized into three different parts, which is the animal migration DB preparation. So this part will mainly be dealing with how we process our ground truth data, our raw data that we're getting for locations. The next part is satellite image dataset download. So for this raw data that we get, how do we actually download the satellite imagery? The third part is ML-ready dataset transformation / packaging, which is how do we actually convert this, like the imagery that we've downloaded to a format where we can feed it into a machine learning model directly. We also have like a legend. So all of the pieces or the blocks in the flowchart represented by like the cylinder and yellow color represent vector files or like a database. So a vector file or a database, not a database separately. So and the other cylinder, the horizontal cylinder, which is in purple, it represents a raster file. So our like images in a way. Blue represents the user parameters. The red represents process or function or code. And then in green, it represents a pandas data frame. You can think of it as a generalized database, but I just put pandas data frame here. And I think it is lagging because of Zoom also using the GPU.
Yeah, probably.
Yeah. Okay. So to get to the first part, so animal migration database preparation. So the whole point of this blog is how do we take our ground truth data, which I have taken to be hypothetically taken to be raw animal GPS coordinates, and how do we convert it to a format that then we can download imagery for. So the first step is getting the data. So we might be getting this through an API. We might be getting this as like a large geo package or a shape file. We don't really know right now. But in this case, I've assumed it's a large file that we got. It will have some geospatial extent. In this case, I just assumed it to be the whole world. For temporal extent, I put 2024 onwards because of base imagery, I think. And then for geometry type, I assume that it's going to be points since like it's going to be singular data. I don't know if they have multiple sensors for one single animal to detect different parts of it, like whales, but I doubt it. But okay. So let's say it's just singular points. So the first step is we remove and we impute missing data. So imputation is basically filling in missing data. What we identify as our missing data can be very different things. So in this context, it could be something like, let's say, the sensor malfunctioned, right? That could be a form of missing data. So we'll have to find a way to remove it, or we'll have to find a way to fill it in some way. And then the next step after that is we select relevant times of interest, areas of interests, and classes. For this, it is a user-dependent task, so we'll have to provide geospatial extents, data ranges, and animals required. So the different classes that we want. So this database might contain data for like 20 animals, but we might only want to focus on turtles, so we select only turtles. After this, we get something I called migration DB, which will have these columns and additional ones. But these are the basic columns that it will have, which will be animal, observation date, and geometry. So this geometry would still be represented by a singular point. And the geospatial extent, I just put as Atlantic Ocean, again, hypothetically, and temporal extent is, again, user selected. The next step is migration DB splitting. So what we want to do is we want to split our large database into smaller GeoJSONs. Why do we want to do that is sort of related to what we looked at earlier, where the yellow ones, these represent this different geospatial tiles. and this black box represents our AOI. One of the issues we have if we have a very large so the first issue that we have is the fact that it might be too computationally heavy to download images with very large AOIs. The other issue we could have is that our AOI ends up being larger than a tile. That again involves like a lot of mosaicing. And also, even if our AOI is smaller than our tile, the larger it is, the more chance of it overlapping with different tiles. So this is one of the reasons that we have to split our overall database into smaller tiles, into smaller GeoJSON, sorry. Okay. So yeah, so to decide, I also wrote some additional information which you can go through. The next thing that we do is we calculate no data percentage per chunk and discard low quality splits. Okay, how would we calculate no data percentage? So let's say, again, going back to this is our AOI, right? Let's say this has points inside of it. So this is representative of multiple animals, right? Yeah, this dot represents like a single animal. So what we can do is we can try and find the data coverage that this image has by calculating the overlap between the points and the box itself. So in some cases, we might want to discard the GeoJSONs. Let's say we have a case such as let's say we have this case. Like a GeoJSON only contains a single point. It might not be very relevant for us to download this GeoJSON because you're downloading a lot of information for just one point, where it might not make sense. So we might want to discard low quality splits. And the other thing that I also wanted to discuss is we can do splitting on like a number of different criterias. One of the ways to do splitting is basically we define a size in meters. Like let's say we want 100 by 100 meters square of GeoJSON. We can specify that and we can split it that way. Another way of splitting the data can be something called geohashes. So to just understand what geohashes are, they are like a quick way of representing geospatial data, and it's like we don't need to get into this like very deeply right now, but they are just a way of quickly querying and quick querying of geospatial data, and different levels represent different spatial sizes. So level one, it divides it out into like 4 pieces. Level two divides it into like smaller, and so on. It can have a number of levels. The reason for this is geohashes make querying very simple because you're sort of just doing string matching rather than like doing polygon operations, which can be very heavy at times. So this is like one way that could be used to split the data as well. And then after that, what we get is we get a final set of GeoJSONs, right? So we have GeoJSON 1, GeoJSON 2, GeoJSON 3, GeoJSON N. So what we want to do after that is we want to download data for each of these GeoJSONs. The next two steps, the satellite image download and the packaging, is for only one single GeoJSON, what has been represented here. So keep in mind, it needs to be represented in times. So the first step that we have is our query. So our query will take our GeoJSON, it will parse it, it will load the GeoJSON, and what it will do is it will load the bounding box. What I mean by it will create the bounding box is that our polygons can be of irregular shape, right? So what we want to do is we want to create like a nice clean square box around it so that we can query with that. With this bounding box, as well as the additional parameters from like the user, so us, we'll have the query dates, we'll have the required sensors, we'll have the required bands, and we'll have the required cloud cover limit. So we can query Earth axis for the given input parameters. And from that, we'll get like a search result. The search result that we got earlier was in like a JSON format from Earth Access, but it might make sense to put this into like a pandas data frame because it allows for like easier operations. That's all. Why would we get multiple search results? The reason we can get multiple search results is what I showed is due to the fact of what I showed you earlier, where we have multiple tiles. So your bounding box might overlap with multiple different tiles. On top of this, we will be providing a date range, right? So within those dates, we'll also get multiple images. So this is why we get multiple results. And what we want to do is we want to calculate, first we want to calculate some parameters. So let's say we calculate the cloud cover and we calculate the overlap percentage for the query box. So by overlap percentage, I mean the query box, the AOI that we have, how much does it overlap with the tile, right? So that is one of the main parameters that we need to decide which tile to use. And also after, we also need to calculate so you'll ask, why did we provide a cloud cover limit here for the query? And why are we calculating it again? So the cloud cover limit here that has been provided is for the whole tile. It is not for our bounding, our AOI. So we have to calculate it again for our own AOI. After this, we filter the search results to find the best satellite images. So how do we define the best satellite images is a very subjective question. And it depends on like the use case. But some of the things that you can use is overlap with the query bounding box. So our AOI, which tile has the largest overlap with our AOI, cloud cover, which tile actually, like which area which area within a bounding box and the tile has like low cloud cover, no data, same thing for cloud cover, but for no data. So this can be missing data, erroneous data, etc. And date proximity. If we want our image to be closer to, let's say, the start date or an end date for some reason, or the observation date itself, this can also be a parameter that can be used to find the best satellite image. But again, there will certainly be additional parameters when we look into it like more deeply, the problem more deeply. After this, we get the filtered search results. And these filtered search results will then be fed into like download and clip functions. So the first thing we do is we download the images. I'll actually change this to tiles. Just for it to not be. Yeah. So we download the tiles from Earth Access and we clip the tiles again to our query bounding box. The reason we're having to do this clipping is because usually the APIs, they'll download the whole tile instead of only your AOI. So we'll need to clip that image again. So let's say we downloaded images for n number of bands and m number of dates. So you can think of it like as a 2D matrix, let's say, of how the data is stored. So you'll have n into m net CDFs with like this form of structure. This is just like a visual representation. There is no need to store the data this way. But the next thing that we want to do is we come to the data fusion part. So earlier we only fused our ground truth to our imagery, like the raster and the vector. But here we might have to do additional fusing. And the reason for that is we have different bands. These can have different resolutions, and we also have different dates. So these dates can also be consolidated into a single image. The date consolidation thing, again, it's a use case dependent thing, whether you want to do it or not. Here I did it for demonstration purposes, but that is not something that we'll be doing necessarily. And it only comes into play if you're using temporal imagery in the first place. So if we're using a system where we're making predictions by only looking at one image, then the temporal fusion part doesn't really matter. Yeah, so what we do is we do the temporal fusion, and then what this will do is it will, so the bands remain constant, so it's still band 1, band 2, band 3, but the dates get compressed into 1. So this is not 1 minus, this is 1, 2. So this will be date 1 to m. So band 1, date 1 to m, band 2, date 1 to m, and so on. The next step that we have to take is to rasterize our ground truth. So this ground truth is coming from our smaller GeoJSON. So we take that ground truth and we convert it into like a raster format, basically matching the resolution of our satellite imagery. This ground truth is then combined with our satellite imagery, which is first in and of itself combined together. So band 1, band 2, band 3, band N, they will be converted to match the same spatial grid, the same spatial resolution, so the same CRS, the reference system, as well as the same spatial resolution. So if we say we want 10 meters, everything will be 10 meters. And the reason we're doing this is because it just makes things very easy to work with. At that point, you can think of it as having at that point you can think of it as a single image with like n channels or n bands. So it makes things very easy afterwards. So we fuse all of our data together, and for one single GeoJSON, this is what we will get: an XCDF with band 1 to N, date 1 to M, and a ground truth mask. And yeah, so since we have this now, we also have to convert it into like an ML ready format. Why do we need to do that? The reason we need to do that is because this image can be very big. So this can still be like 1,000 by 1,000 image, and it doesn't make sense to put into a machine learning model. So what we do is we chunk the data into smaller pieces, which is your time cross n cross n cross c, where t is the temporal dimension of the data. N is n is a user specified parameter, so we define what size we want to keep for the chunking, and c is the number of channels or the number of bands, basically, that we get from the image. And I think I put a couple of reasons of why do we need to chunk our data sets, and I'll just see if I went through all of them. They can be too big. And yeah, so this geospatial context thing we already went through. And yeah, another thing is we want to save our files in a format which is quick and easy to read in cloud applications. So netcdf is very slow to read. The reason for this is like a netcdf file, it contains so much additional data that we do not really need. It contains these XY coordinates. It contains a time coordinate. It contains multiple attributes. We don't need any of this data when we're doing a machine learning task. We just need the image. And I'm speaking of very generalized case. In some cases you might need it, but I'm speaking of a generalized case where you don't. So we only need the image, right? And so we can discard all of this metadata, and we can store it as like a more cloud optimized format. One of them is like ZAR for satellite imagery, but I won't get into that right now. Or we can straight up use like NumPy arrays, TF records, safe tensors, etc. Whatever works, because they're very quick to read. And during your model training, what you want to do is the costly part of the training is the GPU, right? So you want to make sure that you're maximizing the use of your GPU. So for that, to keep your GPU usage high, you want to do the data pre-processing and loading as quickly as possible. And the lighter your input format, the less time you're spending reading it from like a bucket. So this is less of an issue locally, but more of an issue on the cloud. And one potential alternative that I wanted to try, but haven't really gotten the time to, is we save our large like tiles that we have gotten as like a cloud optimized format such as ZAR, and we read these like chunks directly from the large tiles themselves rather than actually saving another transformed format. But again, this is something that I haven't really tested out, and you sort of need to compare it, and you have to do all of this processing during training each time. So not sure if it will be faster or not. That's something to see. Um, But the next thing that we do is after we do this chunking, we get like n chunks of data, let's say. And then we have to do data quality checks. So we compute no data percentage, we compute cloud cover percentage, we compute the class distribution, we compute bandwidth statistics. So I think the first two are pretty clear. The class distribution will allow us to, well, identify chunks which don't have a lot of, which have a lot of no data in terms of classification, so they don't have labeled data. The other thing it will allow us to identify is like the distribution of each chunk itself. And it will be very, very helpful when we're doing our EDA, because you can just use that to get the overall distribution of classes in your data set rather than going through the images again and again. The next thing is bandwidth statistics. So in this, you can save your like the mean, the standard deviation, and any other like max, min, any other statistics that you want, which you feel like would be helpful in identifying outliers, identifying the distribution of your data or the distribution of different bands. So these are some things that you want to get done like in one go. After this, on the basis of these, we discard some images. So the two parameters I put here was just cloud cover limit and no data limit, but there can be additional user inputs that need to be, that need to be taken into consideration. But yeah, these are the two parameters I put for now. And so some images will be discarded, which are like too cloudy, too much in data, the input data seems to be outliers, etc. So once you have discarded the images, you get to the final processing part. During this final processing, you clip the band value to certain ranges. So a lot of the times, let's say you have like a range of 0 to 1000 for like a sensor, but at times you will get erroneous values above it. You want to clip that to some values that you want. This can vary per band. It is not necessary that it will be the same for every band. There can be variation in terms of like each band that you're taking. The next step would be scaling and normalization. So you can select whatever normalization algorithm you want to use. You can do min-max. You can use min-max normalization, or you can use some other form. And then you'll also need like satellite min-max values to scale and normalize your data to like the same range for each of these bands. The next thing is we convert our data to the safe format. So as mentioned earlier, we will be converting our data from like a geospatial format to more of a more machine learning friendly format, let's say. So like an NumPy array, TF record, or like a safe tensor or something similar. ZAR is sort of like a in between where you're not discarding all of the geospatial information, and it's easier, like quicker to read. And it's like I think worth a discussion if that trade off is is it good or not? But yeah, so you'll convert it into a particular save format, and this might require additional steps depending on the actual save format. So TF record, for example, is like horrible to work with, in my opinion. But NumPy is like very straightforward. So you'll need different processing steps. After that, after all of the images have been converted or at least saved locally, uh, what you do is you have a dataset writer function where you pass the dataset save bucket or path, and you have an image writer which uploads these images to the actual bucket, and you have a database writer. So the database writer for each of these images, it is the information data frame, right? So it is gonna keep writing like the different metadata with regards to each image. So so these are some of the columns that I could come up with, but there can be many more, which is the image save path, observation dates, class distribution, cloud cover, no data percentage, etc., etc. So the whole purpose of this is to have as much information as you can in an information data frame, which is very easy to open and read compared to opening like 60,000 images. So it makes sense to to store all of the information that you can think of, which you might need for training as well as for testing later on in this information data frame, so that it just makes your workflow after that easier. And this is like tree structure of the final data set, for example. And I think I also have like a, so this is like a sample thing that I had where this is what your data set might look like, where you have these label files. So when you rasterize your data, you will have, so since it might be rasterized into like a segmentation mask, you'll have for each class, you'll have a mapping value. And then you have like an information data frame. What I can do is I can just quickly read this and show you what this one has. For example, this one, so this one contains file name, year, number of bands, X dimension, Y dimension, time dimension, cloud cover percentage, class value count, identifier, etc. So this is sort of like a thing that you will have at the end. And that is basically it. And I'll just mention that this is not a set thing that we have to do. Like this is just an example to just sort of give you an idea of one, like a hypothetical example of what can be done with the process. But when we work on our use case, we'll be defining the process at that time. But yeah, that's basically it. Yeah. Any questions?